Okay, so this is going to be a probably mega kind of live stream, probably take maybe 2.5 hours. And really for all of you OCR people in the chat, you've done paper one, and I think there were kind of maybe some mixed reviews, if that's kind of fairly polite. There weren't any mistakes, which is obviously great, but I think some people found the questions maybe a bit more challenging, kind of lots of people I heard of maybe running out of time. So yeah, we'll see how it goes. But of course, paper one is a completely separate thing to paper two, and whenever paper one happened, it's happened, it's out of the way. There's no point really talking about it too much. And often what I found is over the years there might be a nice paper one, a hard paper two, or vice versa. So paper one's done, that's out of the way, and now it's all focused on paper two, which I guess is just a little bit of different content. The kind of the questions I've got coming up. Have I seen paper one? I haven't actually seen a physical copy of it. I've heard about it. I've heard about some of the questions, and I've obviously seen the reaction from lots of people. So I haven't actually seen it. But of course, don't worry about it. It's been, it's gone. There's nothing you can do about it. Whatever you did in the exam, that's there. It's going to be marked at the moment, or there's people kind of looking at that, and there's nothing more you can do. All you can do is look forward to paper two. Right, so let's see. People saying they're cooked. Yeah, but that's probably just the heat. You'll be fine next week. It's going to cool down. It's going to be lovely. Now, before I start beginning with this kind of predicted paper I'm going to be working through, it says it underneath here, but basically I am going to be doing a masterclass this Sunday at 10:30 for you if you're doing OCR and you've got your Exploring Physics paper next week. So this is a 2-hour long masterclass that I'm going to be running on Sunday morning. You can book it on my website, which is alevelphysicsonline.com. When you go there, there's a classes booking page. It's £30, but you can get 10% off if you use the code MASTER10, which is the kind of thing in this massive orange kind of thing just beneath me. And of course, for all of you who've got a Premium Plus plan, that gives you 50% of any masterclasses as well. So all pretty good value. And of course, everything today I'm doing is completely free. So if you just want the free content, stay tuned for the next couple of hours. Of course, you can also re-watch it at any time over the next couple of days. Right, somebody says, the last predicted paper was very inaccurate. Yes, this is a thing, right? I am not writing predicted papers. I'm going to be using the PMT one. So this is what they've put together. So Physics and Maths Tutor, you all know the website, lots of good stuff there. This is their predicted paper that you can download completely for free. And I'm not affiliated to PMT in any way other than that they've used some of my material in the past, which is a really kind of good thing that I've kind of shared with them. So this is not paid promotion, it's not me doing it for them, it's just something that I think is a good set of questions. Now, I do not think that these topics are exactly the ones that are going to come up in the exam next week. To do well, you have to understand and revise everything. You cannot rely on a predicted paper to decide what might come up in the future. However, the reason I'm going to use this is partly because people love a title. You're all watching it now. The word predicted means that people watch the video, and that means hopefully I can then share kind of my my tips, my techniques, my explanation of the physics as we go through this. So I don't think that these are the questions that are going to come up, but it's still useful to see how to approach these style of A-level physics questions, because if you take the same approach to whatever's coming up next week and the week after, you're going to be absolutely fine. The AQA Paper 2 walkthrough is going to be tomorrow, and I'm going to do that from 2 o'clock in the afternoon. So yeah, basically the same kind of thing, but tomorrow we've got the AQA crowd in. However, if you're an AQA student or an edXL, if you're doing IB, if you're in Wales, wherever you might be, there's still lots of good physics content, but of course this is really specific for OCR. Right, so yeah, let's begin. So, Exploring Physics, 2 hours, 15 minutes. This is the author, this is PMT. You get all that stuff when you go to the website. Let's have a look at the first bit, which are the multiple choice questions. Which of the following shows the correct base units for the Tesla? So let me just zoom in a bit. So anytime you get a question about like base units and all that good stuff, if you're not sure, you might just remember this. If you've used like my daily workout books, there's a similar question, or exactly the same question there. But if we think about a Tesla, well, this is a unit that we measure magnetic, it's to do with magnetic flux, it's the magnetic field strength, and we know that F is equal to BIL. that's still like a GCSE kind of style kind of equation. So the force is equal to B, which is measured in Tesla, that B field, times the current times length. So we could also say that B is equal to F over IL. And then I want to think about, well, what are the base units for force? Well, force is, the Newton. How can we work that out? Well, I guess if you think about 1 Newton as a force could cause a mass to accelerate, and therefore F equals ma. So we could also express that in kilograms times meters per second squared. Okay, so that's the base unit for force. An amp is what we measure the current in, and the length is measured in meters. So that's the same as kilogram meter second to the minus 2 divided by amp meters. And we can see then that the m's cancel, and if you've got kilogram meter per second squared over amps, that's the same as kilogram second to the minus 2 amp to the minus 1. So that's kind of like my working out. So somebody's saying A, that is the correct answer. Yeah, so this one here, the answer is A. So I've not even looked at those. They're just distracting. They're all too similar. I've got no idea, just from looking at this, which one it might be. And therefore here, the correct answer is A. Okay, Galactica Girly, excellent. Aseb Chubbs. Okay, right, Chubbs, completely the wrong answer. Right, so yeah, basically that's it. So this first one is A, but of course what I'm trying to show now is, you will not get an identical question coming up. It's not predicted, but this would be my approach. If you're not sure, if you can't remember it, write down an equation, think about what all of these base units for all of these things are, and then you can kind of just work out to the side until you get the right answer. And of course you can use all of that space there. Right, so number 2, again, this one here is A, B, C or D. What do you reckon? So a student uses a digital micrometer to measure the diameter of a uniform wire. They recorded 4 readings. The manufacturer's value for the diameter is 0.4 plus or minus 0.01. Which one describes the measurements? So I would say that we've got a lot of measurements which are very close together, and that means what we have is something where we've got quite a high precision. So the precision is going to be high. By the way, I hope this is like the right answer. So basically what I'm going to do is, first of all, just get rid of the things which are definitely incorrect. Now, if you're not sure, you can always use a pencil for this, just to kind of maybe cross stuff out in case you make a mistake. But I'm just going to go straight in with the pen. So we've got a high precision because all of these things are fairly close to one another. However, all of these are slightly lower than what is the kind of the manufacturer's kind of true value. And imagine this is like 0.4 is exactly what they've manufactured it to. So that should be like the true or the real value. And these ones here are different to that, so therefore it's not accurate. So the accuracy is relatively low, so it's not going to be those. Is that right? Yeah, and actually, because those ones have already been kind of scrubbed out, it doesn't really matter what those are, so it has to be low accuracy but high precision. And then of course we've got the percentage difference between the two sets of data. Now the percentage difference is going to be the difference between this data and this data divided by the real value. So the first thing I'm going to do is just work out the mean, and the mean diameter, D, is just going to be those added together. Well, actually, we know because you've got a 38 and a 37, and a 38 and a 37, the mean diameter is going to be 0.375 millimeters. And to work out the percentage difference is going to be equal to the difference between the numbers, so that's 0.40 minus 0.375 divided by the true value, which is 0.40, and that's going to be multiplied by 100. So that would then just be basically that's the same as 2.5 divided by 40 times 100, which is 6. Have I made a mistake there? Let's see. have I made some kind of mistake? So 0.40 minus 0.375 divided by 0.40. Oh, 6.25%. Sorry, my mistake in my calculator. Yeah, 6.25. Galactica Girly says that. Somebody's saying B. And therefore I think the right answer is going to be B. So B is the correct answer for number 2. I probably should have worked through some of these questions before the live stream. By the way, how's everybody getting on? As Max Macy says, how did everyone find paper 1? Are there usually social media logos at the bottom of your paper? I would say, John, no, this one here is just the PMT one. So this is just, and I don't know what that is. I'm not quite sure what that means. Anyway, basically, this one here is the PMT predicted paper. There's going to be no social media, no phones. Don't take your phone in by mistake. Okay. Enjoying the live? Excellent. Cool. Which of the following statements correctly describes the classification of subatomic particles? So leptons are composite particles. Immediately, that can't be true. So again, in the chat, let me know A, B, C or D. What do you reckon the answer that you put down is? Oh yeah, by the way, it's not red wine. This is actually a load of chilled Vimto. It's slightly fizzy, which isn't actually probably great for when I'm kind of talking. But my office is absolutely boiling hot. I've got a fan. I promise you it is not red wine. If this was red wine, you'd be asking for your money back because it looks quite weak. But yeah, basically, it's really hot in my office. I've got a fan by my feet, but I don't want the noise to kind of get in the way of the live stream. So hopefully this can keep me cool. Right, lots of people are saying D. Okay, leptons are composite particles. That's not true, because leptons are fundamental particles, which means they're not made out of anything else. Hadrons are fundamental particles is incorrect, because hadrons are made out of quarks, and also baryons are made out of quarks as well. So a baryon is just something that's made out of 3 quarks. Mesons are a type of hadron consisting of a quark-antiquark pair. That one there is true, and therefore the answer is D. And in a way, it has to be true because the first 3 are incorrect. So leptons, things like electrons or neutrinos, they are just made out of pure electron or pure neutrino. Whereas if you've got something like a proton, which is a baryon, it's made out of 3 quarks. Right. Somebody says there's a question about mesons on University Challenge. It's always nice when there's like a sciencey or a physics question and you can get it right. Okay, so we've got a 230 volt electric heater. The current in the heating element is 8.7 volts. The cost per kilowatt hour is 28 pence. What is the cost of using the heater for 4 hours? So the energy transferred is going to be the power times time, but of course the power is equal to I times V, and so the total energy transferred is equal to ITV. Okay, so the energy transferred is the current times the potential difference to get the power times the time, and that's going to be equal to 8.7 times 4 times 3,600. So this is going to be the time converted from hours into seconds, multiplied by 230. So I'm basically just putting it all in there. So this is equal to 28814,400 joules. However, we want to convert this into kilowatt hour. Do you know what? Hold on, that's a bad way of doing it. So let me do that. Let me do it instead and looking at the energy in kilowatt hours. So, do you know what? Let's just go back. I could divide it by 3.6 times 10 to the 6. Let me just do it again. By the way, everybody's saying C, so I'm assuming that's the correct answer. Let's have a look. So the power is going to be equal to IV, which is 8.7 times 0.230 kilovolts, which is equal to 2.001 kilowatts. and then that means the time, or the energy transferred, which is the power times time, if we're going to work in kilowatts and hours, is just 2.001 kilowatts times 4 hours, which is obviously I can't believe I just did that on my calculator, 8.004 kilowatt hours, and we're going to multiply that by 28 pence, so 0.28 is 2.24 pounds. Because all we did was we multiplied this by 0.28 pounds, and therefore C is the correct answer. So for this one, because I worked in kilowatt hours, I first of all worked out my energy in kilowatts, then I multiplied that by the time in hours to get the total number of kilowatt hours of energy used. There we go. Yeah, right, number 5. An electron enters the uniform magnetic field directed into the plane of the paper. So the field, in that case, is going to be moving away from us. So this is the magnetic field. So I'm just going to draw a diagram here. And what we've got is an electron going into this. So here's my electron, and it's going to be going that way into that. Okay, so I've drawn a diagram. Actually, let me get my Lego. Sorry. You know, there's a bit of a Lego obsession. By the way, check out over there the new rocket. How good is that? Anyway, talking of Lego, here is what you need to do. Start with a diagram. If you start with a diagram, that's the kind of thing that can really help the rest of the question. So this is a diagram I'm drawing. I've just got the field going into the paper. I've got the electron coming to the right. What's the direction of the magnetic force acting on the electron the moment it enters the field? So using Fleming's left-hand rule, we've got first finger field going into the paper. Second finger current is going to be going this way round, because although it's an electron moving to the right, that means the positive or the conventional current is going to the left, and that means my thumb is going to be pointing down, so there'd be a force down, and that means the answer for 5, let's see, we've got Nak Salazar, we've got Max Macy, Amiri, Crin, we've got quite a few other people there getting the right answer of B, and it's going to be towards the bottom of the page, so I think for this one the answer is B. Is that correct? Am I right? Cool. Yeah, so it's not A, the answer is B. Elena, excellent, good stuff. So yeah, basically for this one, you've got the electrons moving to the right, but that means you've got a negative thing going to the right, but this finger here with Fleming's left-hand rule is for the conventional current, which goes positive to negative. So that's why this second finger here should be going this way. So basically that's the way that we say that basically a positive current is moving if you've got a negative current going to the right. First finger field pointing down, and that means my thumb is pointing down, so it's B. Okay, cool. This one here, technetium-99m, comes up all the time. It's used as a tracer. Which of the following describes the decay process and the primary reason for its use? Well, because it's metastable, what happens is the technetium-99m, let's just put like, yeah, that's 99m, basically makes technetium-99, and also it gives out a gamma photon. So it decays via gamma emission, so it's not A and it's not C. And what we don't want is a long half-life. We want to have a short half-life, and then we also want to have something that doesn't ionize too much of the body's tissue, ensuring minimal ionization of internal body tissues. B is the correct answer. So this one here is also B. Excellent, loads of that. Lewis versus Z Physics 2026, paper 3 would be scenes. Yeah, I need to maybe get him in here a bit more. Okay, right, I need to have more Z Physics. By the way, if you want Z Physics, and actually, this is a genuine question. It's obviously me and Z Physics. We are like the kind of the two kings of A-level physics. I know there's other people out there, science shorts and so on. Who are the other physics creators or people that you think I should get in to do more collaboration videos with? So let me know in the chat. Who are the people that you think I should get in to do some videos together or to film more content for me. So who would you like to see sat in this studio doing physics papers or maths papers, whatever else it might be? So yeah, Science Shorts has been mentioned. Yeah, let me know in the chat who you really rate as educators, like people who are real qualified teachers, they know what they're talking about. Who would you like? Science Shorts is a goat. Mark Rober, Brian, yeah, Brian. Okay, Brian Cox, fair play. He can like fill up like the O2 Arena. I don't know if he'd be like coming in or not. Okay, I'm just going to write some of these people down to the side. I see the name Mark coming up quite a lot. Mr. Turnbull Physics. Yeah, don't ask about thoughts on climate change. Okay, Isaac Newton, Einstein. Yeah. Bill Nye, the science guy. Is he still alive? Anyway, we're getting off topic. Let's get back to the proper physics. 7. Oh, lovely. Actually, this one isn't too bad. So, if you've got two resistors of the same resistance in parallel, because there's basically two routes for the electricity to go, their combined resistance could be replaced with a resistor that has a resistance of 30 ohms. So a 60 and a 60, identical resistors, is going to halve the resistance. And now, if you've got a 15 volt supply, lovely negligible internal resistance, if that's 15, then that must mean we'd have, I'll just go to another colour, we'd have 7.5 volts across that, and we'd have 7.5 volts across that, because two identical things are going to share that potential difference equally. What's the power? Well, the power is just equal to VI, so that's just 7.5 times 30. Now, I know I could work that out in my head, but I could make a mistake, so I'm just going to rely on the calculator. That's 225 watts, and then, no, sorry, wrong equation. I'm getting ahead of myself. So, right, so P is equal to I squared R, or it's equal to V squared over R. So that's going to be 7.5 squared divided by 30. I think when it gets too hot, my brain stops working. So 1.875, which is going to be A. So lots of people in the chat there. Elena, Aseb, Nak Salazar, Chubbs, all of you saying that, yeah. Okay, right. Right, Captain Physics. Okay, right, do you know what? I'm writing this down for people I need to kind of contact. And I see we're going very much with a white male kind of teacher kind of thing at the moment. Right, Science Shorts. Yeah, I'll put Science Shorts down as well. He's actually, I think, Science Shorts lives fairly near me, like an hour away, so maybe that's it. Okay, right, let's keep going. Number 8. Wire X and wire Y are made of the same material. Wire X has this length and that diameter. That's got triple the length and double the diameter. Okay, so for this one, I would say that in an exam, there's probably going to be quite a lot of working out. So this is the kind of thing that you need to think about. Is it worth the time, or is this the thing that you kind of skip and you come back to at the end of the paper? Now, I haven't done the question yet, so let's see what's going on. We know we've got something here. No, so basically, we're looking at how the current, so the same power supply, so they're going to have the same voltage, and we've got the current. So basically, we know that the current is equal to V over R. And of course, we know that the resistance of something is equal to rho L over A. So what that means is the resistance is proportional to the length and inversely proportional to the area, and the area is going to be equal to pi d squared over 4, and therefore we can say that the current, or let's put this into here first of all, the resistance is equal to 4 rho L over pi d squared A, and of course the current is equal to V over R, and this is what R is. So that means the current is equal to V times pi d squared A over 4 rho L. Oh no, sorry, we don't need A. Excuse me. Right. Okay. Yeah, so for this one, basically what we can see is that the current is equal to the potential difference times pi d squared over 4 rho L. Now, of course, the thing is, this means that the current is going to be proportional to d squared over L, because we're going to have something with the same value of potential difference because it's the same power supply. Pi is a constant, 4 is a constant, and they're the same material, so rho's a constant. So basically the current is proportional to d squared over L. Now for the first one, the current, well, it's going to be equal to d squared over L. Let's say that's, yeah, proportional to d squared over L, and that's the first one. Now the second one is going to be proportional to something with twice the diameter, so that's 2d squared over 3L, which is equal to 4 over 3 times d squared over L, and d squared over L is equal to I1. So basically I2 is equal to 4 over 3 of I1, and the question is, what's the ratio? Oh, sorry, I should have said IX over IL. So that's IX, that's IL. So IX is equal to this times IY. Oh, do you know what? I'm getting too hot. So that means IY over IX is going to be equal to 3 over 4. And therefore the answer for this one is going to be, was that right? No, sorry. Right, so basically IY is equal to 4 over 3 IX, and that means IY over IX is equal to 4 over 3. Okay, so this means then the answer, looking at these, must be C. Sorry, that wasn't explained so well. Right, some good stuff, by the way, at the moment is... okay, so... somebody says that they can't find any women online teaching A-level physics. We need more women in STEM representation. I think there are some out there, but there's just not as many. I know there's a female physics teacher who does stuff for my ed space. I also know that there's somebody doing a lot of GCSE content for physics. But I'd say in A-level physics, it is massively underrepresented, especially when I know so many female physics teachers. And also there are so many girls who are actually doing A-level physics. I know sometimes in your classes there might only be a small number of girls in your class, but if you look at the whole cohort around the country, there's thousands and thousands of girls doing A-level physics. Yeah, so we've got V Physics, Brooke does physics, yeah, that's the one, she does stuff for my ed space. We've got Primrose Kitten, thanks John, okay, right. Yeah, somebody says Britain's got 3 hot days of good summer weather this year, but you're inside revising. Yeah. Okay, right. Anyway, this is good stuff, by the way. The people you said, these people here, I'm going to contact them after this and try and get some stuff sorted. Okay, a positron and a helium nucleus are separated by a distance of 5 times 10 to the minus 10, 11 in a vacuum. Calculate the magnitude of the electrostatic force between them. This one's lovely. It's just a case of finding the right equation. And I must say, when you are in the exam, double check the equations that you're using, especially when it comes to electric and magnetic fields, because it's so easy to maybe use the wrong thing. So for this one, if we're looking at electric fields, it's the force that we're after, and that's equal to QQ over 4 pi epsilon naught r squared. So F is equal to QQ over 4 pi epsilon naught r squared. So even though you don't have to, it's still a good idea to write down the equation. So we've got a positron, so that's got a charge of +1. So that's 1.6 times 10 to the minus 19. We're going to multiply that by the charge on a helium nucleus, which is going to be +2. So that's going to be 3.2 times 10 to the minus 19. And that's going to be divided by 4 pi. Epsilon naught is 8.85 times 10 to the minus 12. And again, rely on your data sheet, double check everything, because have I written down the right number? Permittivity of free space, 8.85 times 10 to the minus 12. I know it. Multiplied by the distance between them, 5.0 times 10 to the minus 11, all squared. That's it, isn't it? Right. Yeah, okay, so will I ever go to my ed space? No, because I think I've decided I quite like doing this under my own terms. So yeah, I'm not going to go to my ed space, but I'd very happily work with lots of teachers. Lots of people are saying B. So shall I just trust you? Basically, that's the equation that we need. And then, of course, if you do the math, then it should come out to an answer, which I guess is going to be that. So I'm just going to assume that, seriously, the slow-mo, hello again, we've got Mood, Devo, we've got Amari, Elena, all of you, yeah, basically saying B. So B is the right answer. But we get there by writing down the equation, having double-checked it in our equation sheet. We put the numbers in, we double-check the constants in our equation sheet to work this out. Is this the last one? Okay, no, not quite. A beam of monochromatic light passes from air into a dense glass block. Right, people, what do you reckon the answer is? A, B, C, or D? Let's have everybody here. I think it's about 60 people or so in the chat, so it'd be amazing to see 60 people putting in their answer. Okay, so let's imagine we've got this block here, and we've got a beam of light that passes into it, like this. So we've got a certain wavelength of light, and as it goes in, the speed of that wave is going to slow down, and the wave fronts are going to get closer together. Okay, lots of people are saying D. So the frequency decreases. No, the frequency stays the same, so that bit's not true. The speed decreases. Well, that's true, but the frequency increases. That's not true. The speed remains constant. Isn't true, because it's going to be slowing down. The wavelength decreases. That's true. And the frequency remains constant. That's true. And therefore, I guess what this tells us is that the frequency of a wave tells us its colour. So you have red light going in, and it stays red light, even though it's got a shorter wavelength now, but it's got the same frequency, the same number of oscillations per second. So we've got, oh my God, there's so many people here in the chat. That's amazing. Yeah, the frequency never changes. John Smith, perfect. Right, so therefore the answer for this one is D. Right, a nice standard oscilloscope question. Obviously, let's have a bit of praise for behind me. I've got the Lego oscilloscope over there, just sat in the back. Right, so that one there, 100% made out of Lego. Maybe, do I have a problem, or do I need to like just lean into it and just get more Lego science equipment behind me? Right, let's have a look at this one. So, the Y gain is set to 5 volts per division, and the time base is 10 milliseconds per division. So, what's the amplitude? Well, the amplitude is going to be from the midpoint to the peak, and we can see that's equal to 2 divisions, and that means if each one is 5, then that's going to be equal to 10 volts. And I suppose the other thing is, if we want to look at the time period for the wave, the best way to do that is to measure more than one wave. So basically 2 waves is equal to 8 of these, which is this. So basically 2 times the time period is equal to 80 milliseconds. That means the time period is equal to 40. So the best practice isn't just to look at one wave cycle, but to maybe measure 2 or even 2.5. And then of course the frequency is 1 over the time period. So that's going to be 1 over 40 times 10 to the minus 3, because we've got something here in milliseconds. Okay, where did I get a Lego oscilloscope from? I just made it. Yeah. Right. Why are there only 4 likes on the video? Right, if you haven't already done so, do like the video, and you can always subscribe to the channel so you can actually post stuff in the side. By the way, everybody here in the chat that I'm sort of keeping an eye on as we go through, thank you so much for subscribing. That's really good. Okay. Right, so 1 divided by 40 times 10 to the minus 3 is 25. So that's correct, and the amplitude is 10. Therefore, C is the correct answer. I think that's right, isn't it? Yeah, loads of people saying C there. Lego voltmeter. Yeah, I've got a Lego voltmeter behind me as well. More of these, right. Okay, so this one I think is quite tricky actually. An alpha particle with an initial kinetic energy is fired directly to a stationary gold nucleus containing this many nucleons and that many protons. Which of the following provides the best estimate for the distance of the closest approach of the alpha particle to the centre of the gold nucleus? Well, basically this one here is basically where we can say that the initial kinetic energy all goes into that final potential energy between these two things. Okay, and of course the potential energy between the two things, well, I guess this is where we're going to be looking into our data book. We're going to find something. So the energy is equal to QQ over 4 pi epsilon naught r. So this is the equation we're going to use, and therefore we can say the initial kinetic energy is going to be equal to the final potential, electrostatic potential between the two things, electrostatic potential energy between the two things, which is QQ over 4 pi epsilon naught r. So we want to find D, the distance, or the maximum distance, which is going to be the same as r. So we basically can bring the r up here to say that the distance is equal to QQ over 4 pi epsilon naught times that kinetic energy. Okay, so then we got to think about it. So the Q and Q is going to be, one of them, if it's an alpha, has got a charge of 2 times the elementary charge, so that's 2e, and the nucleus has got a charge of 79e, so it can't be this one here, because 197 is just the number of nucleons, so it's not that one there. Then we've got, so that one's right, and that one's right. We've got 4 pi epsilon naught, so they've all got that. And then the other thing we need is the kinetic energy, which is 6 mega electron volts. And I guess what we need to do is convert from mega electron volts into joules. So basically that's going to be 6 divided by 1.6 times 10 to the minus 13. Is that right? No, sorry. 6 times 1.6 times 10 to the minus 13, which is 9.6 times 10 to the minus 19. Yeah, so basically we're going to convert from mega electron volts into joules by multiplying by 1.60 times 10 to the minus 13, because you've got 10 to the minus 19 times 10 to the 6, which is 10 to the minus 13. So that's going to basically the conversion factor. So that's the energy. So the kinetic energy is equal to 9.6 times 10 to the minus 13 joules, which is going to be this one here, and therefore the answer is D. Okay, right, so, right, let's see what people are saying. So, just having a quick look at the chat. Okay, it's just random stuff, isn't it? 26 likes, though. Seriously, 26 likes. That's pretty good now. But I'm hoping that there's at least 5,000 people will watch this before the weekend and before their exam. Where can you buy the shirt? This one here? No, it's custom only. You can't buy them. Right. Can I show the oscilloscope? Go on then. So here we go. This is the Lego oscilloscope. You can see if I just go to this shot, it's all made out of Lego, like the whole thing, including like the screen and all of that. So yeah, basically this is the Lego oscilloscope. Anyway, I'm getting distracted. Right. I haven't actually seen paper 1 yet because of like being. I didn't get a chance to go into school on Friday to see it, and then it's been half term, so I haven't actually seen it. Yeah. Right. Let's do number 13. Let's just keep going with the physics. So a single gamma ray photon interacts with the nucleus and produces an electron-positron pair. So what effectively we have is energy making mass, so some pair production. What's the minimum frequency of this gamma ray photon? So we know that E is equal to mc squared, and I guess the energy is going to be equal to HF. So that's the energy of the photon, and that then makes two different things. And so the total mass of whatever is produced is going to be the mass of the electron plus the mass of a positron, because we're making an electron or a positron and an electron. So that's going to be equal to 2 times the mass of an electron times c squared. So the frequency is going to be 2 times the mass of an electron times c squared divided by h. And that's going to be 2 times 9.11 times 10 to the minus 31 times 3.0 times 10 to the 8 all squared divided by 6.63 times 10 to the minus 34. Okay, so yeah. Simon Polkanoff, yes, okay. Do you know, I should have forgot. Sorry. People are talking about collabs. I should have thought about Simon as well. Yeah. Again, quite a male heavy list. So if anybody's got any good female physics teachers who they've seen, I'd love to have them doing some videos as well. Okay. So this is the answer. What's the answer? People are saying A. So ASEB, Mudivo, seriously, Amari. I think I'm just going to trust your judgment, and you've done the work and actually the calculation. All I do is put that into my calculator, and this gives an answer of A. So this one here, we've got the energy being converted into mass. The energy of that photon is HF, and this makes the mass of two things. Okay, Brooke does physics. Yeah, I think that name's coming up quite a lot. Right, number 14. Yeah, Brooke does physics, I think, has to be like the main A-level physics teacher who is female. But we'll see, there must be more out there. There must be lots of other people doing physics. Right, a parallel beam of X-rays is incident normally on a sample of bone with an attenuation coefficient of 1.2 per centimetre. What's the thickness of the bone required to reduce the intensity of the X-ray beam to 25% of its incident intensity? So lots and lots of words there. I would say, looking at the ultrasound stuff, or sorry, X-ray, I is equal to I naught times e to the minus mu x. Right, so we know that this is going to be 25% of that. So basically 0.25 is equal to 1.00 times e to the minus mu x. So what we're saying is if that was 1, it's now 0.25. Okay, so basically that means that the natural log of 0.25 is equal to minus mu x, and that means x is going to be the same as the natural log of 0.25 divided by minus 1.20. And for this one, I can see the answers are in centimetres, so I'm going to keep my attenuation coefficient in centimetres to the minus 1. Tom Rock's maths, Bison maths. I've already done one of Tom Rock's maths. I need to do another one. Actually, Bison maths, good shout. He's always on holiday though. Every time I see him, he's just on holiday somewhere hot and sunny. So I need to find him when he's back in the UK, when he's back in Manchester. Okay, so the natural log of 0.25 divided by minus 1.2 is equal to 1.155. And therefore the answer for this one, 14, is D. Mudivo, Elena, Aseb, Volcanascus, is it? Basically, Volcana. Yeah, there we go. Right, 15. A monochromatic beam of light with this wavelength is incident normally on a diffraction grating with 400 lines per millimetre. What's the maximum order number of the interference pattern? So we know that n lambda is equal to d sine theta. That's the first thing we know. And effectively, when you've got light going through a diffraction grating, the maximum order, because obviously there's going to be like the 0th and the 1st and then the 2nd, the maximum here must be when this angle theta is equal to 90 degrees, and sine 90 is just 1. So basically, if we said that if theta is equal to 90 degrees, then sine theta is equal to 1, and therefore n lambda is equal to d. And then all we need to do is to find n is look at d over lambda. Now it's got 400 lines per millimetre, so that's the same as 1 divided by 400 times 10 to the 3. So this is a common thing to convert from the number of lines per millimetre to the distance between the lines. Divide that by the wavelength, which is 600 times 10 to the minus 9. So 1 divided by 400, 10 to the 3, divided by 600, 10 to the minus 9, is equal to 4.17. And therefore the biggest number it could be would be n is equal to 4. And so here the answer for this is B. Nicely done, everybody. Yeah, so if they don't give you an angle, you assume it's 90 degrees galactica girly, because what we're looking at is the maximum order we can see. And what this means is that we could have the first, we'd have the 0th, we'd have the 1st, 2nd, 3rd and 4th, but anything more than that, it couldn't exist. It couldn't actually exist on that screen, because to get the 5th order, it would have to basically bend more than 90 degrees. Yeah, so it's the maximum order that we're looking at. And of course, if the maximum order is 5, okay, here's another question. How many bright spots would you see on the screen? So you shine a laser through the diffraction grating. How many spots would you actually see on the screen if the maximum order was 4? Somebody says 9, somebody says 11, 9, 9, 9, 9. Yeah, so basically, if we think about what we'd see, you'd see the 0th order in the middle, and then you'd see the 1st, 2nd, 3rd and 4th, and you'd see the 1st, 2nd, 3rd and 4th. So basically there would be 9 in total. So you've got 4 here, 1 there and 4 there to get a total of 9. And occasionally questions like that do come up. How long have I been talking for? 45 minutes, 48 minutes already, and I still have only done the multiple choice questions. In the real exam, you don't have to be chatting to people, reading comments, and I'm sure you're going to be a lot quicker than that. Just be ruthless with the multiple choice. Don't spend an hour to get those kind of 10 or 15 marks. Instead, go through them quickly. If you're not sure, if you know it's going to take you a long time to do that question, leave it and move on and come back to it at the end of the paper. Okay, by the way, has everybody here seen all of the flashcards I've put together? I've got 500 flashcards over at A-Level Physics online. If you've got a school subscription or a premium plan or a premium plus plan, you can see them at alevelphysicsonline.com/flashcards. And then I've got things like all of the definitions that you need to remember. Okay, yes, there's over 500, and I've made them just for OCR. I've got a separate set for AQA and a separate set for EdXL. Very flash, works really nicely. Yes, somebody's seen them, that's good. Right, what is the work function of a metal? So this one here, they basically give you easy marks, provided you've actually kind of done that. Oh, somebody's saying there's somebody called Josh. So I'm going to write this down. Josh. Cool, right, I'm doing that. Let's see what people have said. The minimum energy required for an electron to be liberated from the surface of a metal. Yes, that's pretty good. So, the minimum energy for an electron to be liberated from the surface of a metal. Yeah, very nice. I think that looks pretty good. Right, liberated. I think it's a good one. Are they OCR verified? I mean, I don't know. I don't think the people at OCR have looked at them, but I'm pretty happy with them. Yeah, basically, I've got like, I don't know, ages. How long have I been teaching for? Over 15 years. Basically, since you guys were little people, since you were toddlers, I've been teaching A-level physics, and therefore, yeah, I reckon just trust the kind of definitions I put up there. Ejected would work as well. Yeah, ejected is a good thing as well. Right. Yeah, I guess you're all little toddlers, weren't you, like 15 years ago? Explain why, for a given monochromatic UV source, the emitted photoelectrons are produced with a range of kinetic energies up to a specific maximum. I think this question goes beyond the what the specification needs you to know for OCR. Now, of course, going back a bit, let me explain this. Say, for example, we've got the energy of the photons, and if they're all monochromatic, that means they've got the same wavelength, and therefore they've got the same frequency. So this is the energy of those photons, and that's going to be equal to the work function plus the maximum kinetic energy. Now, this is basically assuming that we've got an electron that's basically on the atom, which is on the very edge of that material. But of course, there's going to be some electrons which are going to be slightly below that. And of course, we also have the real world to contend with, where things aren't just all perfect and ideal. And therefore, that's the maximum kinetic energy. But what we actually see when we look at the photoelectrons emitted, there's a whole range of them that we actually see. A bit like, I guess in a way, you know, if you think about like an ideal gas, there's a whole range of velocities that the particles might have inside that. And yeah, I would say that what somebody here says, if it's deeper in the metal, it needs a bit of extra energy to move to the surface, and then the leftover kinetic energy is less. Yeah, yeah. Work function is the minimum. Actual energy to liberate is an average higher. Hence, by conservation of energy. Yeah. So I would say that I guess that's the minimum energy. So potentially some atoms might take a bit more, depending on how they're kind of arranged in that real material. What's the best way to phrase this? Some electrons do not start on the surface of the metal, so require more energy to be ejected from the surface. So their kinetic energy would be lower than the max value. Something like that, words to that effect. Okay, right. Okay. Okay, this one here is something that is a way in which we can measure the Planck constant, or that we can actually use this thing here called a vacuum photocell to actually maybe look at the work function of a metal, or to calculate a value for the Planck constant. Now, this is not a standard practical done in school. Often it's easier to use coloured LEDs and just see what kind of potential difference they have when they start emitting light. This is an alternative approach to that. And so we've got lots of information here. Calculate the work function of the alloy in electron volts. So we've got the frequency of the light that's being shone onto it. It says when the PD supplied by the variable power supply is changed to 3.2, the current drops to 0. So effectively, the UV light is shone on the metal plate. That then causes an electron to be emitted, and it's going to basically move off that plate. And if it hits this plate over here, we then have a current in that circuit that we can detect with the ammeter. Now, if the ammeter is reading 0, but there's still photoelectrons being emitted from this plate, that means they're basically going towards this, and then they're basically coming back again, because this has got a certain value of potential difference. And here, when the PD here is equal to 3.2 volts, that means the potential difference between these plates is also equal to 3.2 volts. And this thing here is what we call the stopping potential. So I'm going to call that Vs. So that's the potential difference that stops the current in that circuit. So what we can do is think about the equation that we had before, that HF is equal to phi plus the kinetic energy max. Okay, and we know the frequency of the radiation. We can work out the maximum kinetic energy of those particles, and we can also look at the work function, which is what we're trying to find. So basically the work function is equal to HF minus the kinetic energy max of those particles. But of course, they'll have their maximum kinetic energy here, and if they're moving through a distance due to a force, there's going to be work done on those particles, and the work done to basically slow them down, to stop them, is going to be equal to QV. So basically the work done on those particles is equal to QV, and that's going to be equal to the kinetic energy of the particles that they initially had. So very simply, imagine that the electron had 1 joule of energy, of kinetic energy. We would have to do 1 joule of work on it to basically stop it from hitting that plate. Now, of course, here Q is just going to be the charge on those electrons, so that's E, and the potential difference is going to be Vs, and that's going to be equal to the initial, or the maximum possible kinetic energy they had. So this thing here then means that phi is equal to HF minus E Vs. And if we put the numbers in, this is going to be equal to 6.63 times 10 to the minus 34 times 1.8 times 10 to the 15. So that's going to be the energy of the photon. We're then going to take away 1.60 times 10 to the minus 19, the charge on the electron, multiplied by the stopping potential of 3.2 volts. And I think this is the right thing. Lots of people are saying 4.26. Let's just check. It's not a capacitor, this thing. It's not a capacitor. This is called a vacuum photocell, because you basically got a vacuum inside, so the electrons don't collide with anything. And it's basically a photocell, because I guess light goes in, and then I guess it then acts a bit like a cell, because it then means that we've got a current sort of that flows from it. Okay, now let me just do the calculation. So this is equal to 6.8 times 10 to the minus 19 joules, but then we just need to convert it into electron volts. This is equal to 4.3 electron volts. So I think 4.3 is the right answer, because it's to two significant figures like the raw data that we've got up in the question. So I think significant figures are still important, but we've gone from joules, we then just divide by 1.6 times 10 to the minus 19. Is there a way to get K max with an ammeter? Okay, so hold on. Yeah, okay, right. So this can be used, and this is something I just want to explain briefly. You can do this experiment where basically what you look at is the frequency of light, and then you can measure the kinetic energy of the particles that the photoelectrons that come off. And what you get is a graph that looks like this, where there's an intercept with the x-axis. The reason being that if you plot F there and KE there, we know of course that HF is equal to phi plus KE, and that means then that the kinetic energy is equal to HF minus phi. And if you plot a graph where on the y-axis you have the kinetic energy, and on the x-axis you have the frequency. That means the gradient is equal to the Planck's constant, and the y-intercept is equal to minus phi. So basically this means if you plot a graph where you look at the frequency of radiation on that plate and how that's linked to the kinetic energy of the particles that come off, if we were to follow this line back over here, the y-intercept is equal to minus the work function, and the gradient of this line is going to be equal to h, Planck's constant. So this one here is another way in which we can use a vacuum photocell to work out the value for Planck's constant or the work function. Okay, right. Okay, right, let's keep going. The sun emits radiation with a wavelength of 320 nanometers. Explain with the help of a calculator whether or not photoelectrons will be emitted from the surface of the alloy. So, okay, so basically we know for this one that the work function that we just worked out previously is equal to 4.26 electron volts. And we can work out, basically, is the energy of the photon HF, is that bigger than the work function or not? Has it kind of met this kind of threshold frequency? So, in the previous question, I actually had the answer in joules, so that's equal to 6.8 times 10 to the minus 19 joules. Oh no, the help of a calculation, not the help of a calculator. Okay, right. So, the energy of the photon, E, is equal to HF, which is 6.63 times 10 to the minus 34 times, well, that's also equal to HC over lambda. So we multiply that by 3.0 times 10 to the 8, divide it by the wavelength of 320 times 10 to the minus 9. And this is going to give us then the energy of the photons of that particular radiation. Okay, right. (6.21) times 10 to the minus 19 joules, and therefore what we can say is that the energy of the photon is smaller than the work function, therefore photoelectrons won't be emitted. And for a question like this, it's always good to just kind of write a sentence which is actually answering the question they asked. Okay, right, people here are looking at significant figures. Basically, don't worry too much about significant figures. If you did every question to 3 significant figures, then the worst that can happen is you might lose 1 mark over the whole exam. Ideally, you want to give your final answer for the question to the least significant figure of the data in the question. Sometimes it will clearly ask you to give your answer to a certain number of significant figures or an appropriate number of significant figures. Most of the rest of the time, if you're not sure what to do, probably 3 significant figures is a good rule of thumb. But normally you want to go to the least number of significant figures in the question. And most of the time that's often given as 3. And that's also why in your data book, pretty much all of the constants are given to 3 significant figures as well. It's only when we're maybe looking at the mass of protons and neutrons, where we're maybe like calculating like the mass defect, that it becomes really important. Okay. Oh God, it keeps going on and on, doesn't it? Has everybody got plans this afternoon, or is everybody just kind of locking in and sitting here, kind of just doing this? Right. A student suggests if the intensity of the UV source is doubled, the PD required to reduce the maximum kinetic energy of the photoelectrons to 0 will also double, because the light beam now carries twice as much energy to the surface. So, yeah, so this one, I think this is a fairly standard question about the photoelectric effect, where basically what we see with the photoelectric effect is 1 photon causes there to be 1 photoelectron emitted. And it's basically the fact that light behaves like a particle means that you've got individual particles of light that interact with one particle. In this case, it's the electron. Now, of course, if you were to double the intensity, so basically if intensity is doubled, what that means is you have twice as many photons, and therefore you'd have twice or 2 times the number of photoelectrons being emitted. So you basically get a bigger current. However, what's important is we do know, of course, that the energy of that one photoelectron causes the work function phi plus the kinetic energy, and of course the kinetic energy is going to be linked to the stopping potential. So even though we might have twice as many electrons being emitted from the surface, they all have the same energy, and therefore we'd still have the same value of stopping potential of 3.2 that we saw in that first part of the question. So for this one here, the maximum kinetic energy of the photoelectrons to 0 will also double because the light beam now carries twice as much energy. You can say that basically the current increases, but the energy of each photoelectron is still the same. So there will still be the same stopping potential. Yeah, I think that's pretty much it really, isn't it? Evaluate the statement. It basically means, is that true or not? So it's basically a case of just talk about this. So I think evaluation means maybe, it's a bit vague, and I don't think OCR necessarily phrase it exactly the same way, but basically, is this statement true or not? If it is true, can you justify it? If it's not true, what's the science that you know that basically means that that can't be a true statement? Yeah, cool. And I think if you're doing this in the real exam, so let me just get more Vimto. Do you know what, Vimto, I think it's starting to be my favourite compared to Ribena. I don't know, let me know in the chat. Are you a Ribena or a Vimto person? Or can you not tell the difference? Or do you just have like the freeway squash that you might get from Lidl? Let me know what your favourite is. Right, okay. Okay, that one there, let's move on. Oasis all the way. I don't know, I've not had Oasis for a while. J2O, that's quite expensive, isn't it? Vimto, yeah, okay, right, we'll see. Number 17. Somebody likes water. Oh, that's so boring. I know it's good for you, but it's a boring choice, isn't it? A student uses a microwave transmitter to produce a beam of EM radiation. It's directed at a flat metal plate. So let's just think about what's going on. Vimto is gross. I don't know about that. Okay, here we have our microwave transmitter, and it's going to give out microwaves. We shine it at a metal plate. I'm just going to make it look like that so we know it's a reflector. And then what that means is between the two things, we're going to have a wave that's basically moving this way, and that's going to be superposing with a wave going in the other direction. And what we'll then get is at certain distances we have a standing or stationary wave. So this one here, standard, bog standard, bread and butter physics question, how is the stationary wave formed? So basically what we need to talk about here, I'm not going to put all the words in, but I'm going to say these are the words you need to have. You've basically got, you've got a wave that reflects, and superposes with the coherent wave travelling in the opposite direction. Actually, I might just write it out. So keywords here is the fact that we've got the superposition occurs, where we're basically going to be adding the individual amplitudes of each wave. They're coherent waves, which means they've got the same frequency and a similar amplitude and a constant phase difference. And of course, they're travelling in opposite directions, spelled with two L's in UK English. Okay, let's see what people are saying here. Fanta Orangina. Okay, that's Orangina is kind of more like a thing you have on a holiday, isn't it? Yeah, Peach Monster Ultra. Maybe I need that for my next stream. Maybe I'll have that for Sunday when I'm doing my masterclass in the morning. I'll tell you what, I don't know what the temperature is, but it definitely feels hot in my office today. Okay, basically what then happens is, what else do we need to say really? Yeah, this creates interference pattern. Maybe interference pattern isn't right. This creates an interference pattern as they form a stationary wave. Something like that. Yeah, okay. Right. Yeah, the resultant displacement, yeah, I guess yeah, I think that's right. This creates an interference pattern as they form a stationary wave. The receiver detects a series of maxima and minima. State the names of the positions where the receiver detects the minimum, and explain what happened to what occurs to the wave's amplitude at these points. So basically, at a node, there is zero displacement as the two waves are in antiphase with a phase difference of pi radians. So basically they're kind of out of phase by like half a wavelength, or half the basically one's up, one's down, basically. Right. So when he says that Monster is easily the best drink, does it really have rats in them? I don't know. I reckon Monster would like disinfect a dead rat and you'd still be safe to drink. Yeah. Do I have to mention the phase difference? I don't think you do. What happens to the wave's amplitude at these points? But then basically you need to say that this means destructive interference results in zero amplitude, something like that. Okay, right. Okay, right. So what else shall we say? Is that enough? So again, these ones here, there's lots of examples from past papers. You need to think about the keywords. You've got a node, you've got zero displacement, the two waves, maybe an anti-phase, or there's a phase difference of pi radians. We've got destructive interference resulting in zero amplitude. I reckon there's enough there to kind of get the 3 marks. Right, let's keep moving on. The student measures the distance between the first maxima and the 6th maximum detected by the receiver. This distance is found to be 8 centimetres. Determine the wavelength. So let's just do a couple of waves. Okay, so I've just got, I don't know how long it is, but basically the distance between the first maximum and the 6th maximum, so 1, 2, 3, 4, 5, 6. Is that right? Okay, so the question then is, how many waves is this? So let's think about, from here to here is a node, and that's going to be equal to half a wavelength. So this bit here is equal to a wavelength. We then go to another node, that's another wavelength here. And then we've got another wavelength there. So, oh no, hold on. The first maximum and the 6 maximum. So that's 1, 2, 3, 4, 5, 6. Okay, this bit here. And that's going to be half a wavelength. Does that make sense? So we've basically got one wavelength there. We've got another wavelength there. And that one's equal to half a wavelength because that's from a node to a node. Sorry, antinode to an antinode. So yeah, basically, for this one here, we can say that 2.5 lambda is equal to 8.0 centimeters. And therefore lambda is just going to be 8 divided by 2.5, which is equal to 3.2. And it's given us here a centimetre thing on the answer line, so I'm going to leave that in centimetres as 3.2 centimetres. Okay, all good. 2.5 lambda. Right. The metal plate is replaced by a material that partially reflects 50% of the incident microwave intensity. Explain the effect this has on the intensity of the signal detected at the minima. So initially what we had would be a wave that looked like this, and that would then basically be going with a wave that looked like that. And basically when you've got a similar amplitude, if that's A and that's A, so both of these have the same amplitude, when these two things destructively interfere, what we get is basically nothing, because if that was +2 and that was -2, that would be equal to 0. What we've got now is a slightly different scenario where the first wave is still like this. The reflected wave, though, it says is going to be half the intensity, so it's going to be something like that. Okay, and we want to see what happens at the end. So imagine that had an amplitude equal to 2 centimeters. This had an amplitude equal to 1. The first bit here, we'd still have +1. Then we'd have sort of -1 and then +1. So basically this plus this equals this. And that means we don't have 0 amplitude at the minimum point on that stationary wave. So, right. So, the metal plate is replaced with a material that partially reflects 50% of the incident radiation. This, the intensity of the signal detected at the minima, this increases. To, I guess, what else can we say? Right. The minimum point is so the minimum point is 0 if you've got something that has got 2 coherent waves, but we still have coherent waves, but now they've got different amplitudes. So it's a bit like, imagine having like noise cancelling headphones that don't fully work. They're going to cancel some of the noise, but not completely. So whatever you hear is going to be quieter, but not 0. So now the minimum point on that wave that's formed, it increases to a non-zero value. So at the minima, it's still going to be the minimum value that we hear, but it's not going to be 0. So this increases, and I guess also the intensity of that signal is going to be proportional to the amplitude squared. But of course, if the amplitude goes to half of its original value, that means the intensity is going to be a quarter of the intensity of the loud points. So we could say that the intensity of the signal, this increases to a quarter of the intensity detected at the loudest, or the detected at the maxima. But I think with this we wouldn't hear anything, so it's not a sound wave but it's a microwave. So we can say that basically because the intensity is proportional to the amplitude squared, if you half the amplitude, that means the amplitude squared would be a squared over 4. So the intensity is now going to be a quarter of the maximum intensity. And therefore we can say that this increases to a quarter of the intensity detected at the maxima. I think that's all right. Yeah. So yeah, right. The student suggests that measuring. Shall I try and draw a picture of that? Okay, imagine you had a stationary wave where you had this is like the thing that's emitting the wave, and then you've got a reflected wall over here. What you'd see between the two things, if you had all of the energy being transferred back in the other direction, is you'd see something that looks a bit like this. Okay, and what you'd have is you'd have like the maxima here, and then you'd have the minima down here. So you'd have the antinode and the node. And effectively that's 0, and that's the maximum value. Now, if you had something where you had a big wave going one way and a smaller wave going the other way, I think what you'd see, imagine if it was like a string, it wouldn't be kind of doing this kind of perfect thing. I don't know if I can actually draw it. I'm trying to sort of visualize it. It would be a bit more like the maxima goes up, then it sort of goes down a bit, goes up, down. It goes a bit more like that. And so if you sort of think about how that signal intensity sort of changes as you go along, rather than it being like a maximum and then 0, it would be like a maximum and a non-zero minimum. Then we go up to a maximum again, you'd have a non-zero minimum, and so on. So I think potentially that's more what it might look like. Yeah. Is that right? Yeah. Okay. The student suggests that measuring the distance between 10 successive minima would lead to a more precise value for the wavelength than measuring the distance between just 2. Justify that. Basically, this would decrease the percentage uncertainty. As for the same absolute uncertainty, the measured value is larger. Hopefully that makes sense. It's a bit like if you measure something with a ruler, if you measure something which is 1 centimetre long, or you measure something which is 10 centimetres long, you still have the same absolute uncertainty in that reading, which might be plus or minus 1 millimetre. But if you're measuring something which is 10 millimetres long, that's going to be 10 plus or minus 1, whereas something 100 millimetres long is going to be 100 plus or minus 1. So you've got the same absolute uncertainty, but now we've got a much longer measured value. So for this one, that would have a 10% uncertainty, whereas this one would have a 1% percentage uncertainty. So by measuring a larger distance with the same absolute uncertainty, we'd lower the percentage uncertainty in that thing. All right. Yeah, cool. Oh my God, it is so hot. We've got so many questions to do. We've got, do you know what? Yeah, it's going to be tough next week. Hopefully, though, I am hopeful that with the temperature cooling down next week, you've had like a lovely bit of a holiday after your first kind of couple of weeks of the exam period. Now it's going to cool down, so by the time you go back into your exams next week, everything's going to be cooler. It's nice and wet, so you don't mind being at home working. Yeah. Right, I've got my last bit of Vimto. Let me just get that, and then we're going to go on to question 18. Okay, so the first one is about a capacitor. Let me just check the equations. So, yeah, somebody wants to go to the Lake District. Me too. It sounds lovely there at the moment, up in the hills. Right, so capacitors. We need something for the energy. So the energy stored, W, we've got basically the capacitance, C, and we've got the potential difference, V, and therefore we're going to use the equation that says the energy stored is equal to a half CV squared, or a half V squared C. Okay, I find that a very weird way of the data sheet giving you that equation. A half CV squared sounds so much better. So that's just going to be a half times 4t squared times 50 times 10 to the minus 3, because we've got a millifarad there. So that's going to be 40 squared times 0.5 times 50 times 10 to the minus 3, which is 40. And therefore W, the energy stored, is equal to 40 joules. Nice, easy start. Okay, this is question 18, by the way, and I think it goes up to question 23. I can't believe I'm doing this for free as well. Right, by the way, if you do like this, I am doing another masterclass Sunday morning, 10:30, all aimed at OCR paper 2 revision. So basically just like some of the more tricky topics for this. So if you want to book onto that, there's a code just underneath me that you can use. State and explain how the energy stored would change if the PD across the capacitor was halved. So basically, I think it's pretty easy, and it's like, so basically the energy stored is proportional to V squared. Therefore, if V goes down by 2, the energy stored goes down by a factor of 4, which is equal to 10 joules. Yeah, so basically, if you halve the potential difference for the same capacitor, so C is going to remain constant, it would go from 40 down to 10. So I'd explain this by, I guess, putting it in words. Right, yeah. When's my AQA revision? I'm doing an AQA session like this tomorrow afternoon at 2 o'clock, and AQA is going to be from 1:30 till 3:30 Sunday. So if you want to come along for that as well. Actually, I'm just going to go and check if anybody's actually booked on. Bookings are looking good. Lots of people are booking on in the last hour, which is great. Okay, yeah, so basically this one here, you can say how for the same capacitance and stuff, W is proportional to V squared. So if you halve V, then the energy stored goes down by a factor of 4 from 40 down to 10. And that's what you need to put in words. Okay, right, the next one. The capacitor is discharged through a fixed resistor. Describe how the engineer can safely use the discharge circuit and a graphical method to determine the value of R. Okay, so what you can do for this is like a standard practical, is basically you'd have the capacitor, you'd have a capacitor here, and what you're going to be doing is you have this in a circuit that goes through a resistor, like that, and what you'd have is a voltmeter in parallel to that, and what we know is that V is equal to V naught e to the minus t over RC. Okay, and that means that if we want to know what the value well, I think actually this question is a bit vague about exactly what you need to do. But basically, if you take the natural log of both sides, we've got the natural log of V over V naught is equal to minus T over RC. And I think the question is a bit vague, but to find a value of R, so this means that RC is equal to, yeah, okay, let's work this out. So basically then, that means the natural log of V naught over V is equal to T over RC. Hold on, let's do that in a better way. Hold on, let's think about what we want to do. if we start with this, we can say that the natural log of v is equal to the natural log of v naught minus t over rc. And I guess the standard way of doing this is if we look at this and we look at this, we can say that the natural log of v is equal to minus 1 over rc times t plus the natural log of v naught. Okay, that then means if we plot that on the y-axis, we've got mx plus c. This means that the gradient of that line would be equal to minus 1 over rc, provided we've got a graph where what we do is on the x-axis we plot the time, and on the y-axis we plot the natural log of v at those different times. What we should then get is a negative line, and if you work out the gradient of that line, we can use that to work out the value of r. So basically from this, the gradient is equal to minus 1 over rc, and that means the value of r is going to be equal to minus 1 over the capacitance of that capacitor multiplied by the gradient. Okay, and therefore this question here is a kind of fairly standard approach about looking at the discharge of a capacitor, maybe in this case to work out the resistance of that circuit. So in the real exam, the things that you need to do are draw a circuit diagram. That's absolutely essential. You need to write down the equation and how the equation is linked to y equals mx plus c. You have to do that. I suggest that you draw in a sketch graph to show the shape of it, and then at the end you need to say how you can actually work out the value that it needs from the gradient. The other thing here that you need to think about is what equipment you might use. So a lot of this is based on really obvious things. So if you're measuring the time, you need to state that you're going to be using a stopwatch, potentially. If you're measuring the value for V, you might talk about using a voltmeter. Or maybe a better way than doing that would be to use a voltage probe set up with a data logger, and then of course you can then log the data with the time and the potential difference over time. So yeah, there we go. This one here is all kind of fairly standard, and it's kind of fairly kind of standard method for that. A capacitor is disconnected from the DC supply and connected to an AC power supply, and so a sinusoidal trace is observed on the oscilloscope. What happens to the amplitude of the voltage trace as the frequency of the AC supply is significantly increased? So I guess what it's saying is initially we've got something where we might see, if it's being done slowly, we might see this kind of sinusoidal trace that shows that. If you were to increase the AC supply, oh, this is not a nice question, is it? Right, so what did other people say for this? This isn't as nice a question to draw. I suppose if you were increasing the potential difference, so this is what we have for a normal capacitor, is that you get a shape like this as something is charged up. So this is your value of V, and this is time, and what we have is there's going to be the gradient of this, how quickly it charges up, is going to be related to the time constant, tau, which is equal to R times C. Now, of course, if you are charging something up really quickly, it's never going to get up to the maximum value. So maybe you had a 6-volt supply, but you were charging something up really quickly before you then discharge it. It's never going to get up to 6 volts because it only maybe ever reached like a mid value there. So what I then think you might see is on the trace on the oscilloscope, rather than getting up to kind of the maximum value that we might have got to before, it's not quite going to get there. So it kind of might get to this point before it starts discharging, and then it kind of doesn't discharge fully, and it kind of basically does something like this. Sorry, that's probably not the best thing. So basically what we see is it doesn't have the same amplitude of voltage as the frequency of that increases. Yeah, so I think what you could say is that for this thing here, you might say that the frequency increases on the graph, but the maximum amplitude of the voltage is lower than before, as it doesn't fully charge on each cycle. I think it's difficult here because they haven't given you any numbers about what the capacitance or the time constant for that circuit is and what the kind of frequency is. So I think it's quite hard to judge what might happen because they haven't given you any actual data or any numbers in this thing here. Yeah. So I think that would be my answer there. So the frequency increases on the graph, but the max amplitude of the voltage is lower than before as it doesn't fully charge on each cycle. So it's not going to fully charge or fully discharge. Right, let's keep going. I think we've got, if this is question, oh no, this is D. I think we've got about 4 questions to go. Okay. It says a capacitor is charged back up to 40 volts and then disconnected from the power supply. A dielectric material of relative permittivity is inserted between the plates. So basically, this is what the capacitor was like before. And if we've taken it away from the power supply, we know that it's still going to have a potential difference across it of 40 volts. And whatever charge is on this is going to be the same. So Q should be the same. But the difference is now we've got a different value of capacitance. And looking in the data book, we can see that the capacitance of a capacitor, C, is equal to E naught A over D. So basically the capacitance of that capacitor is related to the permittivity of the material between it. So imagine now what we do is we put another material between this, which is something which is really looked at in a bit more detail by students doing AQA physics, rather than those necessarily doing OCR stuff. So basically the relative permittivity goes from 1 up to 1.4, and therefore the capacitance goes up to 1.4 of the original capacitance. So now the new energy stored in it, I guess, what can we use? We can use W is equal to a half Q squared over C. Is that right? Yeah, let's see. Does the voltage decrease by 1.4? I don't think so. Or should it? It should probably decrease by that much. Yeah, this one's a hard question actually, because if it's disconnected, you'd have the same charge stored on each plate, but you'd have a change in the electric field, so I think the potential difference might decrease. This is where I probably should have worked through the question before I did it live in front of lots of people. So I think if we have we're changing the electric field between the two things, so that might change the potential difference. So I guess initially the charge stored is equal to 2W over... Oh, do you know what? This one here, it's getting too hot. I can't think. Yeah, capacitance and electric fields are the worst topics. Yeah, I think a lot of people agree with that. I am doing a capacitor workshop, by the way, not with this question in it, but I'll be doing that this weekend. Let's go back and say basically the new energy, so the initial energy is going to be equal to, I don't know. Let me just have a quick think. I'm just going to quickly check something and I'll be back in a minute. Okay, right, basically, does this school or office not have aircon? No, it doesn't. It's got a tiny fan that's not really working, and I've just got the window open with lots of air coming in. Yeah, basically, I've ChatGPT'd it just to confirm things. Of course, when you... I think this is probably what I said. Basically, when you've got the two plates, there's going to be a certain charge stored on it. And if the plates are like moved apart or made closer together, or you insert a dielectric, we still have the same charge on the plates. But what we're doing then is, because we're altering the electric field between them, we're going to change the potential difference across them. So let's kind of go with the initial thing. So initially, I'm going to write out all my answers again. So we've got this capacitor here of a certain capacitance, and it stores a certain charge across the plates. Now Q, we can work this out looking in our data book. Q is equal to CV, which initially is a capacitance of 50 microfarads. So that's 50 times 10 to the minus 3 times 40, which is going to give us a charge stored of 2.0 coulombs. Okay, so afterwards, when we've got the dielectric between the plates, what we've got now, so I'm just going to put that dielectric in there. We still have the same value of charge, so Q is going to be equal to 2.0 coulombs. And the capacitance goes up to 1.4, what it was before. So that's going to be 1.4 times 50 times 10 to the minus 3. So that's going to be equal to 1.4 times 50, which is equal to 70 times 10 to the minus 3 farads. Now the new energy stored, W, is going to be equal to a half, and again there's lots of different things we could use. We know we've got Q and we've got C, so that's equal to a half times Q squared over C. So it's 2 farads. Well, I'm just going to put that as 2 squared, divided by the new capacitance, which is 70 times 10 to the minus 3. So that's equal to 28.57 joules. So the new energy stored by the capacitor is 29 joules compared to 40 joules that we had initially. Is that all right? Where did I get 2C from? The answer, okay, right. Yeah, does that make sense? Is ChatGPT allowed in the exams? No, it isn't. but it is actually surprisingly good even for stuff like this, just to kind of give you a bit of just to sort of get you started. So I do think that ChatGPT is good. Maybe Claude could be good as well. I think ChatGPT is pretty good at the moment. I think Claude can do other things. Right, so there we go. That would be my answer to that question there, D. My AQA live stream is going to be tomorrow at 2 o'clock. I'm going to do the PMT predicted paper for that as well. Okay. An engineer is designing a light sensing circuit for a solar-powered garden light. We've got a battery, internal resistance, determine the values of E and... Okay, the engineer builds a circuit using a battery, variable resistor, ammeter, voltmeter and a switch. Draw the circuit diagram for this experiment. So this is going to be my battery. It's got an internal resistance R. And what we're going to do, if I just put a dotted line around this to show that there is some internal resistance, we can connect this up to a ammeter. We can connect it up to a variable resistor. And also, I guess we have a switch over here. And what we want to look at is the terminal PD, or the PD across that component, the external resistance there, and that's it. So basically, we've got an ammeter in series with this component that's going to have a certain value of R. We're going to a voltmeter across it to measure the terminal PD. And then, of course, what this means is we can then basically go on to later, and this isn't part of the question, but if you were to plot a graph where you looked at the terminal PD and the current, we'd have a negative line where the gradient is equal to minus R and the intercept is equal to the EMF of that battery. Okay, explain the purpose of the variable resistor in the circuit. Yeah, okay, the purpose of the variable resistor is to change the resistance of the circuit, so different values of current and terminal PD can be measured. So basically what you want to do is, as you change the external resistance, maybe you make the resistance bigger, we get a lower current in that circuit, and also a lower, as you have a bigger resistance, we'd have a lower value of current and therefore a higher value for that terminal PD. Right, using Kirchhoff's laws prove that the PD across a variable resistor is given by V is equal to E plus IR. So I guess the E is going to be equal to the potential difference across the resistor plus the potential difference across that cell. Okay, and I guess this is what we see as that terminal PD, and the potential difference across the internal part of that thing here is sometimes called lost volts. So let me just say underneath, this thing here is EMF, the electromotive force. This is basically the terminal PD. And this thing here is sometimes called the lost volts. It's referred to that, and it's basically the voltage lost in that cell. But of course, in the actual cell itself, we can represent the internal resistance with little r, and there's going to be a certain current everywhere in that circuit, I. Okay, now if you've got a current going through this thing with a resistance R, we know from V equals IR that the potential difference lost in that thing is going to be equal to I times little r. And so I guess we can say then that the EMF is equal to the terminal PD plus I times little r, and therefore we can say that V is equal to E minus IR. And of course, if we take this equation here, we can say that V is equal to minus RI plus the EMF. And if you plot this on the y-axis and this on the x-axis, then that means the gradient is equal to minus R and the y-intercept is equal to E. So the internal resistance is equal to minus the gradient and the EMF is equal to the y-intercept. That all making sense? Yeah. Okay, good stuff. Some people asking about a dielectric, why is it used? Basically, I will answer all of that Saturday morning at 10:30, where I'm going to be doing a completely free masterclass, all looking at capacitors. Really useful if you're doing AQA or OCR paper 2 next week. And it's basically, let me just type it in the chat. So let me just type it in just now. If you want to get that class for free, oh, hold on, not that, ignore that last thing I just said there. If you use the code capacitor20, then basically the capacitor20 code gets you £20 off the £20 masterclass, so it's basically free. The masterclass is always recorded. The live streams just automatically stay on YouTube, but my masterclasses, I'll basically upload them to an unlisted video on YouTube so you can just rewatch them afterwards. Right, okay. It then says, the next question, the battery has an EMF of 6 volts, internal resistance of 0.8. We've got a fixed 10 ohm resistor and a light dependent resistor. In bright light, the resistance of the LDR is 2 ohms. So I'm just going to put that as 2.0 ohms. Calculate the terminal PD of the battery under these conditions. So for this one, let me have a look. Then basically, sorry, let me just double check something. We can use the equation that says V is equal to E minus IR. Okay, so I guess that means we probably need to work out the current in this circuit. So there's a current that's going to be going everywhere, and that's going to basically be moving around the whole thing. So we know from the equation I is equal to V over R. If we look at the EMF, that's going to be equal to 6.0 volts, and the total resistance of everything in that circuit is going to be 10 plus 2 plus 0.8. So that's 10 plus 2 plus 0.8, and then you've got 6 divided by 12.8 is equal to 0.46875. So that's going to be the current everywhere in that circuit. If we want to look at the PD across these two things, which is the same as the terminal PD, V is just going to be equal to the initial EMF, 6.0, minus this current, 0.46875, times the internal resistance, 0.8, which is equal to 5.625 or 5.6, I think is an appropriate answer for this. Yeah. Yeah, and basically in bright light the resistance of this is 2 ohms, and I just labelled that here within my LDR that we've got in that circuit. Cool. As the light intensity decreases, the resistance of the LDR increases. We know that because if you think about an LDR, what it's going to have is a graph that looks like this when we look at the resistance with maybe the light intensity. So as it gets duller, the resistance increases. Stating and explaining the effect this has on the lost volts across the internal resistor. So basically, as the resistance of the LDR increases, the current in the circuit decreases, and of course the lost volts is equal to IR, and as R is a fixed value for the internal resistance, if you've got a lower current times the same value of R, that means we're going to have a lower value for potential difference being lost. And so therefore the current in the circuit decreases, so lost volts decreases with a lower current and a fixed internal resistance. That makes sense? Yeah. Right, a lot of people asking about this capacitor masterclass that I'm doing. Basically, you can book a place by going to alevelphysicsonline.com. It kind of comes up when you first go to my website, and if you look on the classes page, it also has then all of the classes I'm doing. So this is going to be, there's 10:30 Saturday morning, I'm doing the free masterclass about capacitors. In the afternoon, I've got Joe, who works with me, doing an A-level Edexcel masterclass, but that's all about A-level maths. So if you're doing maths, which you probably are, and you're doing Edexcel maths at A-level, which you probably are, he's going to be doing a masterclass on Saturday afternoon at 1:30. He'll be sat in the same office where I am now. And then Sunday, I've got all my masterclasses. For OCR, it's at 10:30, then AQA is 1:30, then Edexcel is 4:30. You can book everything on the website, and that's all there, it's all good. Yeah, cool. Right, here we go. This next question is, well, it's pretty stormy here last night. We had pretty cool thunderstorms, lots of lightning. The ground is considered to be at zero potential, so that's 0 volts. Draw the electric field between the base of the cloud and the lightning rod. I don't think normally that we get stuff this complicated as a shape, but I guess there'd be a central line here. I probably should do that in a ruler, or at the very least use a pencil, and then we'd have like these kind of field lines. Oh, do you know what? That should be probably, I guess, if we assume it's like basically a flat base of the bottom of the cloud, then these field lines should basically be coming into it parallel. So the field lines come out normal to a surface. They should be at 90 degrees. So really this one should be more like that. And I guess that kind of shows the field. The other thing is, if you put a positive charge in that field, which way would it go? Well, a positive charge would be going towards this. And therefore I guess the field lines should be going towards, away from the, towards the negative thing. So we'd have like field lines that basically look a bit like this. But I think this is quite a complicated shape for something like that. There we go. That right? Cool. Right. Define electric potential at a point. I'm sure this is on one of my many flashcards that I've got. So, what is electric potential? This is, again, it's just different. I'm just going to write it out while I then, yeah, let me just write it out. So, I reckon this is it. Work required to move a charge from infinity to that point. Yeah, that's pretty good. Great to see Galactica Girly still in the chat. The work done per unit charge is important though, because it's not electric potential energy. Electric potential is about the energy per unit charge. And often when we talk about electric fields, we're thinking about maybe a positive test charge. So I guess with something in a gravitational field, mass is always going to be a positive quantity. Here, of course, when you talk about like a positive charge. Okay, Is that all good? Yeah, great stuff. Explain why the electric potential has a negative value at any distance r from a negative point charge. So basically, if you had a negative point charge and you had our positive charge over here, as you move the positive charge away, you're going to have to do work. So you're adding energy per unit charge into this thing until it's a long way away. And eventually, when the two things are far enough away, there's going to be no, like a point at infinity, there'd be no attraction between the two things. And at that point, the electric potential is zero. So basically, you add a number to it until it becomes zero. So therefore, this must have a negative value at this point. Okay, so I've just seen stream health is excellent. Analytics, are people still here? Are people watching me? So I've just seen that something on my screen didn't go so well. Okay, yeah, so so basically electric potential energy is the amount of energy that object might have, but electric potential is the energy per unit charge. Okay, cool. Yeah, it's all working good. Cool. So I just saw all my numbers of people watching this just go to zero, and I was like, have I had like an issue where everything's just overheated? But I think even after 2 hours, we're still going strong. Okay, so explain why the electric potential has a negative value at any distance r from a negative point charge. Basically, you could say that work is done on the positive charge to move it to infinity, where the electric potential would then be zero. And I guess so work is done on the positive charge to move it to infinity, where the electric potential, work is done per unit charge on the positive charge to move it to infinity, where the electric potential would then be zero. Yeah, so I guess this is where if we looked at electric potential with distance, we get something like this. So this is the electric potential, this is the distance, and as you go from maybe this position to this position, we can see that the electric potential increases until eventually it would get to that zero position. Yeah, and it's because we've got a negative and a positive thing, we'd have to be doing work on it. We'd be doing work on this thing as we're moving it further apart. Yeah. In a simplified model of the storm, a pocket of negative charge in the cloud is treated as a point charge. An alpha particle is moving directly away from the centre of this charge. At a distance of 50 metres away, the alpha particle has this speed. Calculate the speed of the alpha particle when it has reached a distance 200 metres away from the pocket of negative charge. Okay, so a lot going on there, but let's start, as it always says, is we're going to start with a diagram. So we've got, this is going to be the cloud that's got a charge Q is equal to minus 0.15 coulombs. And we've got an alpha particle here that's moving away, and it's got a certain mass and it's moving away. And of course the charge on this is going to be, if it's an alpha particle, the charge is going to be equal to 2e. And effectively we know when it's 50 meters away it's going to have a certain value, and then we want to know the speed when it's got to 200 meters away. So it's got a value of v. We want to know the charge on this, or the velocity, when it's at that bigger distance. Okay, so I'm just kind of sort of think about taking a massive sentence of information, put it into a diagram so I can understand it. We've got a half mv squared equals qq over 4 pi epsilon r. Let's have a think about that. So what we know is that the the change in kinetic energy is going to be the same as the change in the electric potential energy of that thing. Okay, and the potential energy at any point, if we look over here, energy is equal to QQ over 4 pi epsilon naught. And if we want to look at the change in gravitational potential energy, so the change in this potential energy is going to be equal to this times 1 over r minus 1 over r. Okay, so we might think about this here being part 1 and this part here being part 2. Okay, so we've got basically 1 over r1 minus 1 over r2. And it doesn't really matter which one is which, because we're just looking at the change, or the size and the change of the potential energy. So the 1 over r part is because basically if we look in the data sheet, the energy in an electric field is equal to QQ over 4 pi epsilon naught r. So we could look at that as the initial energy and the final energy, and basically that might be the initial and that might be the final. So if we use this, we can work out the change in the gravitation, we can look at the change in the electric potential energy. That will be the same as the change in the kinetic energy, and that can then tell us the size of the final velocity. Okay, is this all right? Yeah, so the loss in kinetic energy is going to be the gain in the potential energy. So that's equal to minus, do you know what, let's ignore the sign. So that's going to be 0.15 coulombs, that's the charge on the cloud. We're going to multiply that by 3.2 times 10 to the minus 19, which is going to be the charge on the alpha particle. We're going to divide that by 4 pi times 8.85 times 10 to the minus 12. And then we've got 1 over 50 minus 1 over 200. So that's 1 over R1 and 1 over R2. So I'm going to say that the change in that energy is equal to 6.47 times 10 to the minus 12 joules. Is that correct? Hopefully it is. Yeah, right. So I think that's going to be the change in energy. The final, what else do we need to know? So we've got the mass of it. Okay, so initially, so in stage 1, its kinetic energy is equal to a half mv squared, which is equal to a half times 6.64 times 10 to the minus 27 multiplied by its initial velocity of 6.0 times 10 to the 7 squared. So that's going to be the initial kinetic energy. We're going to take that kinetic energy off it to get its final kinetic energy. So that's 644. So let me just work this out. So the initial kinetic energy is equal to 1.19 times 10 to the minus 11 joules. We're going to take away this number here. And so the final kinetic energy, I'm going to do this one in red, the final kinetic energy is equal to 5.478 times 10 to the minus 12 joules. And of course the speed is going to be equal to 2 times the kinetic energy over the mass square rooted. So if I just multiply that by 2 divided by the mass, and then square root that, this is equal to 4.1 times 10 to the 7. Is that right? Have I got the right answer? Yeah, so this one here, it's just a long thing with lots of kind of repetitive things. And the final velocity is 4.1 times 10 to the 7, when initially it was 6. So basically, as something's moved away, it's basically got slower as it's kind of, because of there's basically a negatively charged thing here, and you've got a positively charged proton. So obviously there's going to be a force pulling it backwards, this attractive force between the two things, and that means it's going to de-accelerate as it goes further away. Yeah, so basically, I think that was the answer there. Is that all right? Not the most exciting, but that's just like your bread and butter kind of calculation. Oh, God. How many more questions have I got? 21, 22, and 23. Okay. Right, so 21. Yeah, 6 marker. I feel about 6 markers probably like all of you think as well. So, okay, so let me just draw a diagram. I'm not going to necessarily explain it all step by step. Initially, we've got a certain length tube that the magnet is going to be falling through. And then we go to something which is twice as long, so it's a bit like this. And again, we're going to have something falling through it. So a spherical permanent magnet is going to be falling through this, and it says the length L is sufficient for the magnet to reach a constant terminal velocity. So that means there's going to be a force down due to its weight, and that there's going to be a force upwards which balances the weight. That's when you've got something L, and now we've got something 2L. It's also going to have the same weight force down, and if it's at terminal velocity, then the force upwards must be the same size. So, so the student makes the following claim. Let me just zoom in on that. It says the magnet takes a significant amount of time to fall because it will be attracted to the copper walls as it descends. Well, that's an untrue statement, because copper is not magnetic, and so the magnet is not attracted to the walls. If you used a longer pipe of length 2L, the exit velocity of the magnet would be exactly the same as it was for length L. Well, that statement is true because it's going to be moving at terminal velocity. And of course, the only forces acting on it, if it's the same weight magnet, there must be the same size force acting upwards. It's going to have the same value of terminal velocity, and therefore it would exit at the same speed. Okay, do you have to know what metals are magnetic and what aren't? You learnt this at GCSE, but you should know that copper is not magnetic. However, what we have here is a really good example of Lenz's law, and this is something that you have to know the definition of. So with Lenz's law, what we're going to have is, this is about something opposing the change that caused it. Now, if you've got the magnet moving next to copper, what we're going to have is we've got basically a conductor and a changing magnetic field. And when you've got a conductor and a changing magnetic field, looking at what we have over here, there's an equation that says the EMF is equal to minus delta phi over delta t. So what we have is a changing magnetic field with regard to time, and that means we're going to be inducing an EMF. Now, if you've got an EMF, that means there's going to be a potential difference or a voltage, but you only get a current when you've got a complete circuit. And here, because we've got a copper tube, it's going to be a good conductor, and therefore we're going to have a current. And of course, when you've got a current, that's basically moving charges. And if you've got moving charges, we're therefore going to have a magnetic field. And basically, there's going to be a magnetic field in the copper pipe that is opposing the change that caused it. So it's going to be opposing the motion of this. So just as much as you've got a weight force acting down, there's going to be an upwards force due to the magnetic field that's basically induced. And then what you've got is effectively the magnet will be causing a magnetic field in that tube where the opposite poles, or the same poles, are going to be facing the same direction. So there'd be like, if you had the north end of the magnet at the bottom, this would then be causing there to be a north end at the top of the tube, which is basically repelling it. Okay, So, yeah, people are saying stuff here about what are things which are magnetic. Iron, cobalt, nickel, that's basically it. You just need to know or remember that copper is not magnetic, but iron and steel are. Okay, so basically you've got this magnetic field here, therefore that this opposes motion. And therefore that's going to be then linked to Lenz's law. And it might be that if you have a real question like this, you're going to get maybe a mark for explaining about the EMF and Faraday's law. You'll have another mark for like just basically defining or just writing down what Lenz's law is. And of course you can then say in the question, this first thing is not true, but the second thing is, if you kind of think about the forces acting on the object. Okay, I'm not going to write my whole answer down because I want to get through this few, an empty page. A household smoke detector uses americium, which is an alpha emitter with a half-life of 432 years. Calculate the decay constant in seconds to the -1 for americium 241. Again, a good place to start is just look through your data book, find the equations or the things which are to do with nuclear fields, radioactivity. So we know here that the activity A is equal to lambda n. Okay, so that's the first thing. The other thing we know is that the natural log of 2 is equal to lambda t a half. Okay, so if you're not sure where to begin, just write down all of the equations. Now initially, we don't know the activity and we don't know the number of particles there, but we do know the half-life. And so we can basically say that lambda, which is a decay constant, is equal to the natural log of 2 over the half-life. And the half-life is going to be 432 years, and then we just need to multiply that by the number of seconds in a year. So that would be 365 days times 24 hours times 3,600 seconds in an hour. So let me just work that out. Whatever it is, let me do that better. Why would they use the same symbol for wavelength and decay constant when there are so many other Greek letters? Good question. It's just that's what happens. It's just physics, and there'll be some good reasons over time. (5.0878 times 10 to the minus 11). Yeah, so I reckon this is equal to 5.09 times 10 to the minus 11 seconds to the minus 1. It's just the way it is, just like we use rho for density and we use rho for resistivity, because a lot of the other Greek letters are already used for other things as well. But that's a good question, ASEB. Calculate the initial activity of the radioactive sample. So, in order to work out the activity, we're going to use this equation here. And we need to know the number of actual things. Now it says here we've got the mass of it is equal to 0.20 micrograms. And I guess what we need to think about is, if we know the mass, can we work out the number of moles? And if we know the number of moles, can we therefore work out the number of particles? And we can. So basically the number of moles is equal to the mass divided by the molar mass. So that's going to be 0.20 by 10 to the minus 6, because it's micrograms, and the molar mass, if it's americium 241, would be 241, and I guess that tends to be the molar mass per gram, isn't it? So we've got 0.2 times 10 to the minus 6 divided by 241. Oh, sorry. This is equal to 8.2 or 30 times 10 to the minus 10 moles. And of course we know the number of particles is equal to the number of moles times Avogadro's number. So if I multiply this by 6.02 times 10 to the 23, this is equal to 5.00 by 10 to the 14. I think. Is that right? Let me just have a quick double check. Yeah, so basically then, the activity is equal to the decay constant, 5.09 times 10 to the minus 11, times by the number of particles, so 5.00 by 10 to the 14, and I guess that's then equal to 2.5 times 10 to the 4 per second. So yeah, 25.4 kilobecquerels. But I'm going to say 2.5 times 10 to the 4 becquerels is the right answer, because it needs to be given to 2 decimal places, like the raw data. And so actually just having a look at what PMT did, they gave it to 3, but I think 2 would be a more appropriate answer. So there we go. Right. Okay. Is anybody still there? Anybody still watching? Yeah. Somebody says, Ali says, I think paper 2 has more standard calculation questions, whereas paper 1, there's more intuitive content, so they made the calculations quite unique and hard. Yeah. Okay, people are watching. Seriously, Aaron, John Smith is still here. You're here. Excellent. Good. Right. There's nothing you need to get involved with every question. Each alpha particle has a kinetic energy of 5.49 mega electron volts. Calculate the initial power dissipated by radiation from this source. So, initially then, we had that many things happening per second. So basically, the initial activity, I'm going to put 2.543 times 10 to the 4 was the activity. And if we multiply this by, so that's basically the number of things per second. They each had this kinetic energy, so the power is going to be equal to the energy per unit time. So let's just imagine the time is equal to 1 second. If we multiply that by 5.49, and then we need to convert from mega electron volts into joules. And so basically that's just the same as that, divided by 1.6 times 10 to the minus 13. No, sorry, times 1.6 times 10 to the minus 13. This is equal to 2.23 times 10 to the minus 8. So I think that's going to be 2.2 times 10 to the minus 8 watts. So a relatively low amount of power. Okay, right. The next question then says, a technician evaluates the worst case scenario where a student eats it and it's trapped in some soft tissue. Calculate the total energy in joules absorbed by this tissue over a 24-hour period. So the energy is going to be equal to the power times time, which is just that 2.23 times 10 to the minus 8 multiplied by 24 by 3600, which seems a bit of a weird question. And what I'm doing each time is keeping my raw data. So although I gave my final answer as 2.2, I've got the numbers saved to my calculator for the next calculation. This is equal to 1.9 times 10 to the minus 3 joules. So basically a very, very small amount of energy. There we go. Right. The technician suggests that if the source was instead a beta emitter of the same activity, the risk to the person would be reduced even if the total energy release was the same. So we're going to basically this one here is about comparing the effects of alpha and beta radiation within the body. So I guess what you want to say, okay, here we say, so, oh God, this does happen. So somebody says in the chat, ASAB says, when your class did the radioactive practical, one kid dropped the source. Don't name any names. I suspect it wasn't you if you're just, if you're letting me know what happened to them. To be honest, it's not really a big deal. You just check the source is okay. You put a Geiger counter over where it was dropped to check there's no contamination, and then it's like Yeah, not a big deal. I reckon chemistry is a lot more. There's been a lot more people injured in chemistry experiments in school when they touch hot Bunsen burners or they get acid on their skin, they get like a small rash or stuff like that. So I reckon what you do in chemistry, it's so much more risky than the small radioactive sources that we have in schools in physics. Okay, compare the effects of alpha and beta radiation within the body. Again, I'm not going to write out the whole thing, but if you think about alpha and you compare that to beta, alpha is basically highly ionizing, and that means it's going to cause damage to the cells nearby. Beta is less ionizing, but I guess the other thing we need to think about is how penetrating they are, and basically we can say that alpha is very short range, whereas beta is more penetrating, so it's got a longer range. So what that means is alpha will basically damage tissue next to it because it's highly ionizing, it doesn't go very far, so it can cause lots of very, very localized damage. Beta will cause less damage to the body and it's going to be spread over a much larger area. So beta might be less risk to the person. Yeah. Cool, right. Here we go, the chemistry things. Somebody said when their boiling tube melted and ruined all your results. Yeah, that happens, you know. These things happen, it's all part of it. And I've probably broken a huge amount of chemistry equipment with bits of glass I've just used improperly, burnt things snapped and all that kind of good stuff. Right, there you go. So basically that's what you want to kind of have in your answer. You want to kind of compare the two things, you know, which one therefore in this scenario would cause the most damage. Cool. People talking about burning bags with, some people in the chat talking about biology now, so dropping acid on a bag and it burned a massive hole. Yeah, pretty good. Right. Okay, next question here. A radiographer uses an ultrasound probe to determine the thickness of a patient's liver. The probe contains a piezoelectric crystal used to both emit and detect ultrasound pulses. How is it used to produce pulses of ultrasound? So basically, what you have with a piezoelectric material is you basically have a link between the dimensions of something and the potential difference applied across it. So it might be that this is what something looks like, and when you apply a potential difference across it, it might stretch like this. So you can see it's basically stretched each side. And that means if you have a varying potential difference, which is alternating, meaning it's like maybe positive and negative, what we can do is this thing here can basically oscillate backwards and forwards. And then of course that means it can give out a mechanical longitudinal wave. And of course the frequency of this wave is going to be the same as the frequency of the AC supply. So if you put in a signal which has got a frequency of 20,000 hertz, we'd get a 20,000 hertz wave coming out. So that's kind of like basically the upper part of a sound wave. If you had a 50,000 hertz AC signal, we'd have a 50,000 hertz wave given out, which is an ultrasound. So that's basically how a piezoelectric crystal works. And of course, the same thing happens the other way. So if you've got a crystal and you have a wave that's hitting it, effectively that crystal is going to cause this thing to move back and forwards. And when you've got the movement of a piezoelectric crystal, there's then going to be a potential difference across it. And the potential difference will have the frequency equal to the frequency of the signal that it's actually hitting. So that's why we can use it as a transducer. So it can both transmit a wave and it can also detect a wave as well. So what happens is the crystal will give out a pulse of a wave for a very short amount of time, and then it waits for that pulse to come back and then it can detect what's coming back. So that's why we use this. So somebody says, are piezoelectric crystals in the spec? Is it in the specification? Let me see what ChatGPT says. For the OCR Spec A-level physics course, do students need to know about piezoelectric crystals?
No, piezoelectric crystals aren't a required topic for the OCRA spec. While you do need to understand various properties of materials and some applications of electrical phenomena. Piezoelectric effects are more of an extension topic or contextual example rather than a core learning requirement.
Did everybody get that? Basically, I think it's not so needed. Is it needed for AQA physics?
For AQA A-level physics, it's the same story. Piezoelectricity isn't on the core specification either.
Well, basically, you know about it now. Okay, I don't know if I trust ChatGPT there. I'm pretty sure you need to know about it. If you just give me 1 second, I'm just going to look on the actual specification for OCR. So what I'm doing now, you can't see it, but I'm just on my website. If I look at the full specification, and then I'm just going to do yeah, actually, ChatGPT was wrong there. You do need to know for OCR-A, it says here that you need to know about the piezoelectric effect. You need to know about an ultrasound transducer as a device that emits and receives ultrasound. So therefore, this question here is absolutely valid, and that answer that ChatGPT gave wasn't good. So basically, you cannot trust ChatGPT for everything. I think that's kind of hopefully highlighting that. So it is on the specification. You need to understand the piezoelectric effect and how that's used in particular in the transducer for ultrasound. Yeah. So there you go. A lot of people saying that is, it is on the spec. ChatGPT wasn't correct there. Okay, the patient's liver is located beneath a layer of fat. The ultrasound probe emits a pulse of intensity I0. Okay, so we've got the acoustic impedance of fat and the acoustic impedance of liver. I can never remember the equation, so it's kind of like Z1, Z2 minus Z1, basically, whatever that is. So the intensity reflected over the initial intensity is equal to Z2 minus Z1 over Z2 plus Z1, and that's all going to be squared. So how much of it is reflected? Well, you've got, let's just call this one, to be honest, it doesn't matter which is Z1 and Z2. Let's call that 1 and that 2. So 2 minus 1 is going to be 1.55 minus 1.38. And that's all going to be squared over 1.55 plus 1.38. And what I'm doing here is basically, that's basically 0.17 squared over 2.93 squared. Okay, now of course I could write this in as 10 to the 6, but because we've got 10 to the 6 over 10 to the 6, it doesn't really matter. So you've got 0.17 squared divided by 2.93 squared is equal to 3.36 times 10 to the minus 3, but that's basically the ratio of the two things. So I need to multiply that by 100 to get the percentage as 0.337%. Okay, so that's my answer for that one. Because basically this is just the ratio of reflected to the original amount. And if we want the percentage amount, we need to have it, we need to multiply that answer by 100 to get it like that. And therefore 0.34 is good, although I would say that we've got 3 significant figures up here. So that's 3 significant figures. So that's why my answer is also given to 3 significant figures. All good? Right. Basically, that's the answer there. And you can see that basically because these two numbers are very similar, we've got a very small number divided by a large number, and that's why only a small fraction or a small percentage is going to be reflected. Oh God, we haven't finished yet. It just keeps going. Right. Has anybody been here for the full 2.5 hours so far? I think I do see a lot of your names, so that's amazing if I've just been here in the background just chatting to you. Hopefully this is like kind of getting you to kind of come along on Sunday as well. Yes. Me. Very good, yes. And people have been here, and again, it's seriously Galactica Girly, Aseb, lots of people here. It's great to see you. Ali as well. Yeah, a lot of your names are really familiar, so that's good. Okay. Explain why the calculated value means that the ultrasound will be able to produce an accurate image of the internal structure of the liver. Basically, it means that most of the ultrasound signal is transmitted into the liver. And basically, this means in the internal structure of the liver, where there's going to be a bigger difference in that acoustic impedance, there's going to be a much greater proportion of reflected intensity of ultrasound, and therefore we can use that to actually image what's inside. Okay, so most of the ultrasound signal is transmitted into the liver. So it can be partially reflected there. To image its internal structure. There we go. I think that's it pretty much. Yeah, somebody says, are there any more of these lives? I'm going to do a free capacitor thing 10:30 on Saturday morning. Use the code capacitor20 at checkout. Capacitor20 gets you £20 off a £20 class, so it's basically free. Yeah, somebody else could put the code in there, that'd be great. And also, I do have a paid thing, but it's only like 30 quid for 2 hours, which I think is pretty good value for like what you might get from it. Cool. Thank you very much for the code. Okay, thank you. Right. An A scan is used to measure the depth of the liver. The ultrasound pulse has a frequency of 3.5 megahertz. We've got the speed here. So basically what this means is we send out a signal and then we get a signal back again. And this allows us to work out how far away something is. And we know that the time between the transmitted and the received pulse is 130 times 10 to the minus 6 seconds. And that's the time it takes for it to go there and back again. I suppose the other thing we need to know about this is basically a simple speed equals distance over time. So that means the distance is equal to v over t, and it goes at 1540 meters per second because it's in a solid material, so it travels quite quickly. And the time it takes to go there and back is 130 times 10 to the minus 6. So if I do that calculation, that means that can't be right. Speed equals distance over time. Oh yeah, sorry. I got the most simple thing wrong. Okay, the displacement is equal to v times t. Sorry, that should be 1540 multiplied by 130 times 10 to the minus 6. I know the chat is going to be telling me I'm wrong. Okay, right, so basically 1540 times 130 times 10 to the minus 6 means the total distance it's travelled is 0.200 meters. However, that's to go there and back again. So what I need to do is divide that by 2 to get the distance there to the other side. So the thickness of the liver here is 0.100 meters. So effectively, you've got a 10 centimeter thick liver, but what we've done here, so imagine my liver is 10 centimeters thick. This is the time it's taken to go there and then come back again. So it's gone 20 centimeters through the liver, which means the liver must be 10 centimeters thick. Excellent. Is it divided by 2? Okay, yes it is. And that's a mistake that lots of people forget. And finally, a student suggests that the resolution of the image can be improved by increasing the frequency. A second student says that a B scan would be more useful. Evaluate these considering the resolution and the depth of penetration required for the scan. Now I would say that's a lot of space to do 3 marks. The first one is a B scan is definitely going to be much better than an A scan. So that's definitely, I'm definitely sure about that. This one here, I'm not so sure about. So let's do the B scan first of all, get the easy marks. So basically a B scan shows a 2D image of the structure. So it would be easier to diagnose any issues with the patient. Because basically an A scan basically just tells you how far away, how big the object might be, or maybe where there's like something inside that. You basically just get a graph, but it doesn't really explain what's going on. Whereas a B scan is much more like the kind of picture that people share when they've got a new baby, and it's kind of like this B scan, you can actually make out something inside, and that's why it's going to be much more useful. Yeah, and a B scan is just made by adding all the data from lots of A scans together, and it gives you that B scan image. The other thing is about the resolution, and I think that this one here is a bit more tricky and doesn't often come up in OCR. I think what it says here is that if you've got a shorter wavelength, we'd have less diffraction. So if you've got like if you've got a low frequency, then basically the wave kind of spreads out like that. Okay, if you've got a higher frequency, we get a much more directed wave, and that means it's easier when you're sending this through the body to point it at the bits that you need. So basically a higher frequency means that the wave is less diffracted. So you get a better resolution. Image. There we go, that's it pretty much. So when you've got a higher frequency wave, there's going to be less spreading out of that thing. So it basically, when it hits the other side of that internal object inside the body and then it bounces back again, you're going to get a much clearer image because it's going to be a much better resolution. And I think that's about it. Right, I've been here for 2 and a bit hours, 2 3/4 hours. I will be doing a much shorter thing on Sunday when hopefully it's going to be a lot cooler in my office. If you do want to come along to any of my masterclasses I've got one this coming Sunday, which is the day before your Exploring Physics paper, so that's £30 for 2 hours starting at 10:30. I'm doing exactly the same the weekend after on the Sunday, where I'm going to do something about unified physics, the paper 3, so I'll do another kind of masterclass for that. Yeah, and I basically think that's it. So if you like anything I've done, do make sure that you kind of come and see me over at A-Level Physics Online. I've got loads of videos there. I explain every topic. I've got loads of worked example videos where I walk through OCR papers, including OCR Exploring Physics. So I've got all of that on my website. I've got model work solutions, I've got flashcards, I've got videos that explain the whole course. Basically everything you need to get ready for your real paper 2, it's all there. But yeah, thank you for joining me. It's great to have you here either in the live stream or watching this on demand. I've got loads of stuff coming up. If you haven't already done so, head over to A-Level Physics Online. You can sign up to my newsletter, which is free, and then that means you get emailed about all the latest bits and pieces. And yeah, hopefully I'll see a lot of you very, very soon. If not, I really hope it goes well for your exams. So yeah, good luck this week coming up, and hopefully see a lot of you again